If you remember, last class we discussed mostly about the questions related to first law of thermodynamics. We'll continue with few more questions as well as some content that is required for solving these questions. See, check out first thing is about how to calculate the work done in chemical reactions. See, chemical reactions generally carry out at constant temperature and pressure, or in certain cases it might be constant temperature and volume also. If it is at constant temperature and volume, usually there is no work done because volume is constant. Okay. So our condition is mostly about constant temperature and pressure condition. Now, in that case, one thing we do is that we assume whatever the gases that are involved in it, they are all ideal gases. Whether they are on the reactant side or on the product side, they are all ideal gases. Second thing, the volume of solids or liquids compared to that of volume of the gases is negligible. Got it? So that's why wherever you have solids or liquids, we'll just simply neglect their volume and accordingly check out what are the other gases involved. Based on the gases volume, we will figure out how much is the work being done. For instance, if I have a chemical reaction as simple as A plus B giving C plus D, and I need to figure out how much is the work done in this particular reaction or in the process where the chemical reaction is taking place, what is the work done? Then the work done will be minus P external into delta V, and delta V is the volume that must have changed. Okay. Now, PV will be equal to nRT because considering all of them are ideal gases. That means any change in pressure and volume will be the change in number of moles or temperature. Since temperature is constant, RT will come out and delta Ng will be observed. So which means if it is a chemical reaction, instead of minus P del V, we can simply write this as delta Ng RT. Now what is delta Ng means here? Delta Ng here represents total number of stoichiometric sum of stoichiometric coefficients of the products minus sum of stoichiometric coefficients of the reactants, considering all of these are coefficients of the gases. Okay, this is how we can calculate what is the work done. Now, for any chemical reactions, we can simply figure out what would be the work done or what will be the work on the system based on the sign of the work. Check out. If there is N2 plus 3H2 giving 2NH3, this is a reaction that's happening. Delta Ng will be equal to product minus the reactant. So 2 minus 4. 2 minus 4 is minus 2. Since it is minus 2, and sorry, there is minus here. Okay. So minus of minus will become plus. So work done is positive. Positive work done implies that there is a contraction happening. Okay. Clear? So compression is happening here. So during the system here, considering it is at constant pressure, it will start getting contracted. Next, PCl5 is giving PCl3 plus Cl2. Delta Ng is plus 1, which means the work has to be negative, which means there is an expansion happening during the reaction. Okay. Calcium carbonate, this side is solid, this is gas. So delta Ng, you will only check out for gases. Product, you have 1 mole. Reactant, you have 0 gaseous moles. So delta Ng is 1. Work done is negative. Here also expansion is expected. H2O is solid and liquid. If you compare that, in such cases, delta Ng is not something which we can compare, but we can compare delta V as the volume of the product, in this case, which is liquid minus volume of the solid. This is the way you can figure out delta V. And now you notice liquid's volume would be lesser than volume of the solid. So overall volume will decrease. So this is about the overall volume. I mean delta V will decrease here. Okay. So if delta V is less, which means, work done will be negative. Clear? Sorry, work done in this case will be positive. Yeah. Okay, volume is decreasing. Next, if you have diamond to graphite, if you notice, then the volume will be more because the density of diamond is more, density of graphite is less. So if density is less, the volume occupied is more. So which means the change in delta V is actually positive. So volume is kind of increasing here as you go from reactants to products. So as volume is increasing, work is done by the system. So expansion will take place. So work is negative in this case. If delta Ng is 0 for all the gaseous reactions, then work is also 0. And I can say at constant temperature and volume, work done will be equal to 0. Clear, everyone? So this is the way for any chemical reactions you can figure out based on whatever the information that is being provided, what will be the work done here. Okay. Now let's slowly get into more problem solvings related to work done, heat. Let's get more comfortable with this area. Okay. So I suggest you guys can try solving along with me. Check out what is given in the question and how we can solve that. See, as the question reads, we need to calculate work and heat in joules and delta U, that is internal energy change, for each process starting from A to B, B to C, and C to A. The information given is about pressure versus volume graph, and units are in bar and liters. Bar and liter units are given. So, in that case, how do we calculate the work? So, first, what we can do, we will first try to figure out one by one what is the work done, what is delta U, and what is heat at every point. So, first, let us say path AB, path A to B. Path A to B is given as isothermal. Isothermal implies, this is isothermal, which implies delta T is 0. If delta T is 0, definitely delta U from A to B is 0. If that is 0, then Q A to B will be equal to minus W A to B. Now, work done from A to B can be calculated using isothermal expansion formula, which is minus 2.303 nRT log of V2 by V1. See what is all the information that is being given here, correct? So if you have noticed that the number of moles in this case is not mentioned, okay? So always in such cases take it as 1. We don't have to, I mean, it has been given, sorry. But by chance, if it is not given, usually take it as 1 and try to solve it. And now temperature, how do we figure out the temperature, how much it is? Since we do not know the temperature, but I know what is the initial pressure and initial volume, I can use that data, or I can know what is the final pressure and final volume. I can use that data as well. So here I can write the same formula as minus 2.303 into N into R into T can be written as PV by P1 V1 by NR. Okay. So that log of V2 by V1. So you can see now number of moles are actually not necessary in the question. So that would be equal to minus 2.303 into P1 V1 into log of V2 by V1. So 2.303 into P1 V1. P1 is 8, V1 is 4. 8 into 4 into log of 16 by 4, which is minus 2.303 into 24 into log of 4. Log of 4 is 0.6. Now, all of this information, whatever we are getting, is in actually ATM liter. Okay. So this is an expansion. That's why the negative value is observed. And then Q of AB will be equal to minus W, which is equal to minus plus 2.303 into zero point 0.6 into 24 ATM liter. Imagine if at all I have to write this in joules, because question asked is in joules. So 2.303 into zero point 0.6 into 24. 1 ATM liter is 101.3 joules. So this would be in joules answer. Correct? This is how you calculate the, heat from A to B. Now let's see from B to A how we can solve. Now delta U from B to A. How will you do that? Check out. This is happening at a constant pressure term. We are checking this is happening at a constant pressure term. At a constant pressure term, for delta U, we do not have much formulas except for NCV delta T. So I can write this as NCV into delta T. Delta T can be written as T2 or TB here. TB, no, sorry, TC. TC minus TB. This is the temperatures for which you are trying to figure out, isn't it? B to C. Sorry, this is B to C. Okay. So from here I can write N into CV into temperature can be written again as, PC VC by NR minus PB VB by NR. So if I bring these terms outwards, so we'll get CV by R into pressure is constant. PC is equal to PB. So pressure can also be brought out. That will be equal to VC minus VB. So how much is the pressure here? 2 bar. So 2 into CV by R into VC is 4 minus 16. 4 minus 16. So that will be equal to 24 CV by R. So this is what is delta U. Okay. CV value is already given to us. So it will be equal to 3 by 2. Okay. So this will come out to be 36. Clear? Now, what is the value of this 36 here, because R and R got cancelled? Volumes what I have taken, the pressure what I have taken is actually in ATM liter. So again, this is in ATM liter units. This will be delta U BC. Okay. Now delta U is what we learned. How much will be the work done? We know that work done is simply the area under the curve here. This much is will be the work done. So work done of BC will be equal to area under the curve is how much? 2 units. That is P, which is constant, into delta V with minus sign. So minus 2 into delta V is 4 minus 16. So this is plus 24 ATM liter. ATM liter. So QBC will be equal to delta UBC minus WBC, which is equal to, now here we are getting this as minus. So we were getting the delta UB as minus. So this is minus 36 minus of 24. Got it? So that makes it 60 minus 60 ATM liter. This will be the QBC. So heat is being released out. Please check everybody if you have got these values. And lastly, if you notice, for work done in the case of C to A, work done from C to A, that is 0. Q from C to A will be equal to plus delta U from C to A, which is equal to NCV, temperature TA, minus Tc, Ta minus Tc, which can be again written as NCV into PAVA by NR minus PCVC by NR. Again, N will get cancelled, CV by R will be remained, and V is constant here, so I can pull it down. So it will be PA minus PC. So if you simply substitute that, you will be able to get what is the value of QCA or delta U. Please check. I hope all the processes are clear here. Right, shall we go ahead? I got this, beta. Right. See the next question here. 2 moles of an ideal gas, CV value is given, was compressed adiabatically against a constant pressure of 2 atm, which was initially at 350 kelvins and 1 atm. The work done on the gas in this process is how much? Have you noticed that initial pressure being 1 atm and the external pressure is 2 atm? So this is something which is helping us to understand this is an irreversible change. Correct? For a reversible change, the external and internal pressure should be almost the same. So here this is an irreversible adiabatic process. We are talking about irreversible adiabatic process. And number of moles given is 2. CV value is given as 5 by 2 R. These are the given values. T1, temperature T1 is given as 350 kelvins. P1 is given as 1 atm. P external is given as 2 atm. Using this information, I can solve one thing, that work done W will be simply equal to minus P external into delta V. So P external will be equal to minus P external is 2 into delta V is V2 minus V1. Okay. V1 we can know very easily because we know that uh, P1 is given, T1 is given, number of moles are constant. So we can calculate V1. But how do we get V2? Because V2 information is not much given here. Correct? In such case, there is one thing we can do. We just know for this is something which I told you earlier. For an irreversible adiabatic process, we have only one equation. That is, work done is equal to delta U. This is the only information we have. So minus P external into V2 minus V1, which is the work done, is equal to delta U, which is N CV T2 minus T1. So using this information, first let us try to figure out what will be the T2 value. And knowing the T2 value, we can calculate what is the value of V1. I mean V2. If we get to know that, then it becomes more easy. Okay. Or since our objective is not to figure out what is the volume, because in the question it is not given like calculate the volume. Let us write this equation only in terms of temperatures. So this I can write it as minus 2 into nRT2 by P2 minus nRT1 by P1. Now, what is the information that is unknown here? First, number of moles and R. This is common. It will come out. T2 by P2 minus T1 by P1. Now, if you notice that the T1 is given, P1 is given, P2 will be same as the external pressure, isn't it? Because that's when the process will stop. So P2 and this 2 value will be same. So the only unknown here, the only unknown value here is this one. Okay, this is the only unknown one. T2 is the unknown. So we'll try to figure out T2 and substitute that back, so we will get the answer. So check this out. So what we can do, this is the equation we have. So I'm using that same equation here. So what do we have? Minus p external is 2 into V2. We just wrote this entire thing as this way. So let me take out that part, into NR multiplied by T2 divided by P2. P2 is also 2, minus T1, which is 350 divided by 2. Sorry, divided by 1. P1 is 1. And that is equal to N into CV. CV can be written because it is of 5 by 2 R given. 5 by 2 R into T2 minus T1, which is 350. Okay. So notice what all things will get cancelled here. N, R, both of them are getting cancelled. Okay. Now let me multiply the 2 inside now. With minus sign I have to multiply. So I'll get minus T2 plus 700, 350, yeah, 700, clear. That is equal to, let me take it to the inside here, 5T2 by 2 and minus 350 times of 5. This is what we have. Okay. And you can see 5T2 by 2 is larger than this T2. So I'll take this T2 to the right hand side. So I will get this as 5T2 by 2 plus T2.
But,
Yes, Vita.
but that should be 350 into 5 by 2, right?
1 second. Say it again.
That should be 350 multiplied by 5 divided by 2.
Yeah, sorry. This is 2 here. 2 I forgot. Okay. So now we have 5T2 by 2 plus T2. And here we have 700 plus 350 into 5 divided by 2. This is what we have. Clear? Using this, we can calculate what is the T2 value here. Okay. So what we are getting is 7T2 by 2. That is equal to, okay. So how much is this value? Let me just calculate and tell you. So 350 to 5 divided by 2, 875 plus 700, 1575. So 1575. Okay. So that multiplied by 2 divided by 7. So 450. So temperature T2 is coming out to be 450 kelvins. Correct. We got the temperature term, so we can simply use that, substitute it back and calculate work done. So work is equal to minus 2 into how many moles we took? 2 into R. R you always write at the end based on how the questions options are, whether they are in joules or not, or calories or something. So T2 now we got it as 450 divided by 2 minus 350 divided by 1. Okay. So it's clearly that it is 700 minus 450, right? Which is 250 by 2. 2 will get cancelled. So 2 into 250 into R into, that's it. 1, 2 will get cancelled. Okay, denominator and numerator we can get cancelled there. So it is minus 500 R. Now check out how the answer is given. Sorry, plus 500 R. Okay, so this will become plus 500 R. Now, if the question was given in calories, because this was a previous year question which was given in calories, R was given in calories. So therefore, 2. So if you multiply 2, so we'll get 1000 calories. Okay. If it is joules, then you have to multiply 8.314. Okay. So 8.314 into 500. So which is 4157 in joules. I hope the type of question is clear, everybody. Please make a note of it. Try to see, this is an important type which is very, very frequently asked both in mains and advanced. Please check this question. The next one, 2 moles of an ideal gas, gamma values given, was allowed to expand reversibly and adiabatically from 1 liter at 527 degrees to 32 liters. The molar enthalpy change of the gas is how much? Okay. So whatever the given information is, let us write that part. So here the hint what you need to catch up is it is reversible adiabatic process. That is the first thing we need to catch. Since it is reversible adiabatic process, so TV raised to power of gamma minus 1 is equal to constant is valid. So we can use that information. Okay. So for that we require temperature and volume information along with gamma. So T1 is given 527 plus 273, making it as 800 kelvins. Next, V1 is given. I think it is starting with 1 liter, and we need to figure out what is the temperature T2 given the volume V2 is 32 liters. So from here, using this information, I can write T2 V2 raised to power of gamma minus 1 is equal to T1 V1 raised to power of gamma minus 1. So T2 is equal to T1, which is 800 into 1 by 32 raised to power of gamma, which is 1.4. So 1.4, I can write this as, um, uh, 7 by 5, correct? So it shows that it is a diatomic gas. Okay. So I can write this as 7 by 5 minus 1. So which makes it as 800 into 1 by 32 into, this will be 2 by 5. Got it? So that is T2 is equal to 800 into 1 by 2 raised to power of 5 into 2 by 5. So which is 800 into 1 by 4 makes it as 200 kelvins. So final temperature to which, because it is an expansion that is happening, temperature is bound to decrease. So this will be the final temperature. Once you get temperature, the question is asked about delta H. You know that delta H can be written as NCP delta T. So let's first calculate Cp. Cp is equal to Cv plus R. Okay. And you know that this is a diatomic gas. So definitely if gamma is coming out to be 1.4, which means which is 7 by 5, which implies Cv has to be 5R by 2 and Cp has to be 7R by 2. So therefore, Cp is 7R by 2. And number of moles, that is given 2 moles. So 2 into 7R by 2 into delta T. So final temperature is 200. Initial temperature was 800. So that makes it 7 into 600 into R. So how much is that? 4200 into R. Okay. This will be the value. Again, depending upon what is given to you, you check out. If the question is given in terms of calories, multiply that with 2. If it is in joules, 8.314. I request all of you to check once carefully. Yeah, let's go ahead. I'm assuming all of you must have got this. See the next one. In a reversible adiabatic process of an ideal monoatomic gas, the final volume is 8 times the initial volume. The ratio of final temperature to the initial temperature is how much? Okay. This is a very similar one. I suppose you can try it out once. Okay. Check out the ratio. It's not that difficult, everybody. Try it once. See this one. TV raised to power of gamma minus 1 is constant. So T2 V2 raised to power of gamma minus 1 is equal to T1 V1 raised to power of gamma minus 1. Okay. So we need to find out the ratio of final temperature to initial temperature. So which is T2 by T1, which is equal to V1 by V2 raised to power of gamma minus 1. Okay. So volume is 8 times the initial one. So 1 by 8 by gamma, which is for monoatomic gas. For monoatomic gas, you know that it is 5 by 3. So 5 by 3 minus 1. So which is equal to 1 by 8 into this goes 2 by 3. So which is 1 by 2 raised to power of 2, which is 1 by 4. So T2 by T1 is simply 1 by 4 ratio. Okay. See the next one. 1 mole of monoatomic gas at temperature T is expanded from 1 liter to 2 liter adiabatically under a constant external pressure of 1 atm. The final temperature of the gas in kelvins is how much? So read the question. When you read the question thoroughly, there is one thing you realize that there is nowhere it is supporting reversible adiabatic conditions. So it has to be a natural process. It has to be an irreversible adiabatic process. Correct. That is the one thing you need to realize. Irreversible adiabatic process. Since it is irreversible adiabatic process, you cannot simply relate T raised to power of minus 1 is constant. This kind of equations you cannot use. And like we discussed earlier, for irreversible adiabatic process, there are not much of a support of equations except for one equation. So let us use that one equation only. W is equal to delta U. This is the only delta U. This is the only equation which we have. So minus P external into V2 minus V1 is equal to, plus N CV T2 minus T1. This is the only thing which we can use. Okay, so I need to express that final temperature in terms of T. So let's see that. So external pressure is 1 atm into volume is final volume is 2 minus 1 is equal to number of moles are 1 and CV it is a monoatomic gas, so that will be 3 by 2 R 3 by 2 R into T2 minus T. So this entire thing goes one time here. I mean, minus 1 here. So I will have this as plus 2 by minus T2 minus T is equal to, this will go 2 by 3 R. So therefore, T2 will be equal to T plus 2 by 3 R. Okay, sorry. R is in the denominator. R. Okay. So this is the final equation which you will get. Minus, my mistake. T minus 2 by 3 R. Check. See the next one now. 1 mole of ammonia at 27 degrees is expanded under reversible adiabatic condition to make volume 8 times. Find the final temperature and work done. Okay. So here I think you got enough hints. You know what is the process. Please try that and complete it. Right. So I assume that the last question, most of you should have got it by now. Okay. So final temperature in this case is coming out to be 150 kelvins, and work done in this case is coming out to be minus 450 R. Please check if you have got this. To the next one. For an ideal monoatomic gas, if Cm is equal to 3R, what is the type of process we call it? And what is the relation of PV? What is the relation? Cm is equal to Cv plus R by 1 minus X. That's what we expect, right? And this is given as 3R, which is equal to 3 by 2R plus R by 1 minus X. So find X here. So you'll get to know what is the process, isn't it? If X is equal to 1, PV raised to power of 1 is equal to constant. So that means it is isothermal. If X is coming out to be 0, that means pressure is constant, which means isobaric. If X is infinity, which means isochoric. If X is something else other than gamma values, right? That means it has to be polytropic process. That's it. So find X now. So from here, if you calculate X, I think you should get 1 by 3. Please solve and check, everybody. So which means this is supposed to be PV raised to power of 1 by 3 is equal to constant. So what type of process it is? Polytropic process. And the relation between PV is PV raised to power of 1 by 3. Got that? Right. So let's see this now. Any particular uh, expansion that is happening, but outside being vacuum, right? Then obviously inside there is a pressure existing, but outside there is complete vacuum. So there is no P external to operate. If P external is not there, then the work done will be zero. And since, once and since there is nothing externally, there will not be any heat which will be absorbed, or there will not be any heat which is given out, which means Q is also zero. If W is 0, Q is 0, definitely delta U will be equal to 0. If delta U is 0, considering inside is ideal gas, imagine if there is an ideal gas. So then it has to be NCV delta T. And if NCV delta T is 0, that means delta T is 0. If delta T is 0, delta H will be 0. It is a process where you can notice that Q, W, delta U, delta H, almost all the parameters which are defining the, you know, uh, heat exchange, they are all 0. So I can say that this process is something like an isothermal irreversible expansion. It is isothermal irreversible expansion. Okay. And also because Q is 0, it is an adiabatic irreversible expansion as well. So it is a process which is both adiabatic as well as isothermal, and both of them are irreversible in this case. Clear? But what is there in the system which might be still changing? One thing, volume is changing. Volume is continuously increasing. Second thing, pressure of the gas inside is decreasing. Okay, this is what is free expansion meant. Whenever you see free expansion, that means this is what you should be able to bring it into your mind. Clear, beta? Right. Now, there is two parts which we can split thermodynamics into. First one is first law, then we have second law. But before going into the second law, let us go through thermochemistry part. That means when instead of having a non-reactive gas, what if there are some reactive mixtures within the system? Then how does they operate? So if you learn this, if you understand these terms properly, then it becomes easier for us to, digest the second law also. In fact, second law becomes more easier to study because we can directly apply on chemical reactions after that. Okay. So let us quickly go through thermochemistry terminologies mainly. Okay. This part of chemistry is mostly about terms. Got it? So let me tell you what exactly by definition thermochemistry gives us. It is about change, heat change carried carried out in reactions. Heat change uh, carried out in reactions, and generally the heat is called as, and it is called as, and it is called as heat of reaction. Simply, terminology that is used is heat of reaction. Okay. Now see, whenever there is a chemical reaction involved, reaction can happen either at constant temperature or constant pressure, but most importantly, this would happen at constant temperature and pressure. This is one condition, or constant temperature and volume. These are mainly two conditions at which we observe chemical reactions. Most of the time in chemical reactions, we try to keep the temperature always constant. Only the pressure and volumes are changing. Okay. Then the heat that is being, involved in this reaction, carried in or out of the reaction, that is called as delta H of the reaction. Okay. Delta H is also known as the enthalpy of the reaction. If delta H of the reaction being positive, we call it as an endothermic reaction, and heat is absorbed in this case. And delta H is less than 0, it is exothermic, heat is released in this case. Okay. So keep it simple, heat will be absorbed or heat is released here. Okay. Graphically, if you notice, I mean, if at all I have to represent it more graphical point of view, check it out like this. If we have to write this as how much enthalpy is changing with respect to reaction coordinates. Reaction coordinate means how the reaction is changing from reactants towards product. That is called reaction coordinates. So definitely the reactants are supposed to have higher energy, products are supposed to have lower energy if it is delta H being less than 0, which is exothermic. Okay. And similarly, if we have similar kind of a graph wherein this is product and this is reactant, and the above one is product and this is greater than 0, then it is endothermic reaction. So graphically you need to understand one thing, how reactant to product is changing. Clear? Now notice, whenever we talk about heat exchange or heat of the reaction, what are the factors that influence the or affect the heat of the reaction? One is temperature, definitely, then pressure and volume. These three definitely affect the heat of reaction, how much heat it is been accepting or absorbing or releasing. This can be dependent on temperature, pressure, and volume terms. Second thing is, what is the physical state of the reactants or products? Are your reactants being solid, liquid, or gas. For example, water when it is in liquid state trying to convert into vapor state, then the heat required may be different. Okay, as compared to Alexa, stop. Okay, as compared to that of heat which is being, uh, uh, heat which is being required from H2O being solid to gas. Got it? So in these cases, if the physical condition of the reactants and products are different, then also it will affect the heat. Okay. The other part which will affect is the allotropic nature of the component. For example, if you have phosphorus, if you are taking P4, phosphorus is P4 structure, but it has many allotropes. If you have white allotrope, you have red allotrope, you have black allotrope. So the structural features of the molecule will be different. P4 molecule in a white form is different than red and then black. In that case also amount of heat involved in the reaction will be different. Okay. And the last factor is how much is the amount of components involved, that is number of moles. If the number of moles are more, then the heat content required might be more or release might be more. Okay. So these are four basic observations that you will notice. Okay. So let me just point out here factors, okay, affecting heat of reaction. I'll write it in simple terms here. First factor is temperature, pressure, volume. Okay. Second factor, what did I say? Physical state. Physical state of reactants or products. Third factor, what did I tell you? This is about allotropic forms. Allotropic forms. Fourth factor, amount of components. Basically, I took these options directly from a JE question. This was asked before, so remember it. This is a very generic part because these are the same factors we'll be discussing while we discuss chemical equilibrium or ionic equilibrium or electrochemistry everywhere. So wherever there is a chemical reaction involved, these are very common factors that will be affecting the heat of reaction. Correct? So these are directly asked in exam. What are the factors affecting? So remember this. Clear? Next. If at all we have a chemical reaction like A plus B giving C plus D and the heat evolved is called as delta H of the reaction, then this delta H of the reaction by definition is the total amount of enthalpies of the products minus total amount of the enthalpies of the reactants. This is the way you can write it down. Clear? So this is what we call it as delta H of the reaction. Okay? Clear? Now we need to figure out what is the enthalpies of the uh, element C, enthalpies of elements D, enthalpy of element A, and enthalpy of element B. Okay. And not just that, just like how we have delta H of the reaction being, enthalpies of the products minus enthalpies of the reactants. We can use this delta H with respect to U and PV because we know that H is equal to U plus PV. So which means any change in delta H should be change in delta U and change in PV. Okay. Now in this case, if you notice, what is the PV change? Earlier we studied for work done. The PV change can be written as delta NGRT. So therefore, delta H can be written as delta U plus NGRT, which represent delta PV. And delta NG is products minus reactant. But all this should be in gaseous state. All these elemental forms should be in gaseous state. Clear, everybody? Now, before going further into detail about, what is standard enthalpy and all of that. So see how the questions are being typically asked in simple terms, how we can solve these questions. Check out one question, I'll add it up here. Calculate heat of reaction at constant volume at temperature is 19 degrees Celsius if heat of the reaction at constant pressure is 631 kilocalories for combustion of for combustion of glucose. This is glucose, C6H12O6. Okay. Now the first thing you need to understand is that if there is a heat released at constant volume, okay, remember at constant volume there is no work done. So the heat released is at constant volume will only change internal energy. Is that clear? So that means heat released at constant volume means delta U, or directly hinting towards delta U. Similarly, released at constant pressure, that is hinting at delta H. So heat released, both things you need to understand, delta H and delta U. Once again. Hello. Right, sorry, check it out. So delta H in this case is given as 631 Kelvin, or sorry, kilocalories. And you know the formula delta H is equal to delta U plus delta NGRT. Since you are making a combustion, just try to figure out what is the reaction. So this plus enough of O2 gives CO2 and H2O. Any organic compound will give you that. Delta Ng in this case is 6, which is a number of moles minus reactant number of moles. See, this is liquid, this is liquid. So you don't have to worry about these two terms. So 6 minus 6 is 0. So delta H is equal to delta U, which is equal to 631 kilocalories. Clear? Now let me tell you what exactly is this standard states. Okay. Got it? See, whenever we say something is a standard enthalpy of formation, standard heat of formation, correct? That means what is the change in the enthalpy that accompanies the formation of one mole of a compound from its elemental standards? What do you mean by elemental standards? That means their core existence. How is that existence on the earth or in the earth crust, wherever it is been found? For example, if at all you have to standardize something, if they are gases, and if you are measuring at their 1 bar, at 1 bar you are keeping it so that its chemical reaction can be learned, then that means you are putting those gases at standard condition, standard pressure condition. If they are chemical solutions, that means they have multiple components in it and it has certain concentration in it. In that case, the concentration need to be represented in molarity and it should be maintained at 1 molar. If you are maintaining it at 1 molar, that means it is a standard solution. Okay. Now, temperature is not a standard value. Okay. But practical purposes, temperature is considered as ambient temperature being standard. And the ambient temperature is 25 degrees centigrade, also known as the room temperature. Okay. And whenever there is a standard condition, all the parameters to which we are representing their standard values, you should always add this not along with it. Okay. The not represent that you are talking about, you know, energy changes at constant at standard conditions. Clear? Starting with first, what exactly standard heat of formation, delta H of formation. Standard heat of formation means 1 mole of a substance forming from constitutional elements in their stable state of aggregates. Okay, that means when they are existing in aggregates, what is the stable form of various elements? For example, carbon's most stable form is graphite, while hydrogen's most stable form is H2 gas. So this is a constitutional form of hydrogen. This is a constitutional form of carbon. Only when they mix together to produce 1 mole of methane, then this particular reaction, delta H of the reaction will be equal to delta H of formation of CH4 minus delta H of formation of this minus 2 times of delta H of formation of H2. Now, since the delta H of formation of all the elemental forms is assumed to be 0, this is a basic assumption that we are taking, that in their naturally most stable form or the referential form, we consider them to be 0. If they are 0, see this, if they are 0, then what is delta H of the reaction's value? That value will be delta H of formation of CH4. So in simple terms, the formation enthalpy, the standard formation enthalpy of a substance is same as delta H of the reaction when you make the chemical reaction from their basic constituent elements. Clear, everybody? Did you get the idea about what is delta H of formation means? Okay, it's a referential form. It's a referential form saying that this reference is considering that the delta H of formation of all the standard elemental forms of all the elements is 0. Okay. Which of this delta H of formation is being 0? For which of them we consider them to be 0? Let's see this. Okay. Starting with H2. How do we write that? This is how we write it. That is delta H of formation of H2. That value is 0. Okay. Similarly, F2, Cl2, N2, O2, Br2. Br2, when you have Br2 in liquid state is 0. This state need to be mentioned as well. Okay. Similarly, if it comes to sulfur, delta H of formation for sulfur being rhombic because it has many allotropic forms. The rhombic allotropic form is 0. Got it? Rhombic allotropic form is 0. Okay. And when it comes to phosphorus white, P for white is 0. I2 in solid state is 0. Okay. Arsenic in its gray form is 0. Gray allotrope is 0. Tin in its white allotropic form is 0. Copper, zinc, sodium, lithium, all these metals in their basic solid state is 0. And only one important part out of all of this, in ions, there is only one ion which has 0, that is H plus in aqueous state. The H plus in aqueous state is 0. So that means delta H of formation of H plus ions in aqueous state that is considered to be 0. Okay, these are the elemental forms, okay, which are having delta H of formation being 0. Now notice this one. If at all I have a reaction like N2 plus 3H2 giving 2NH3, you know that N2 is the elemental form in a gaseous state. Hydrogen in a gaseous state is also elemental form. So I'm getting the product in the elemental form here. So delta H of reaction, let's say, is X. Then what will be delta H of formation of ammonia? If at all I have to find it for ammonia. Now you know that if at all I need to find that, first I need to write products minus reactant. So you can see product is delta H of formation of ammonia minus, sorry, 2 times here. 2 times of delta H of formation of ammonia minus delta H of formation of nitrogen plus 3 times of delta H of formation of X, that is equal to X. Correct? That entire thing is equal to X. Now, because these are standard values, so this is 0, this is 0. So that makes 2 times of delta H of formation of ammonia is equal to X. So delta H of formation of ammonia is X by 2, which is delta H of the given reaction by 2. Clear? Now, if you notice, suppose I have to write the elemental form for various, compounds, right, or substances. How do I write that? For example, I want to write H2SO4 in liquid state. What should be the elemental formation uh, for formation of H2SO4? What should be the chemical reaction supporting to it? This is what hydrogen must come from H2 gas, oxygen must come from O2 gas, sulfur must come from rhombic sulfur, that too in solid state. So S8 rhombic solid. So when you combine these and you report 1 mole of H2SO4, not multiple moles, only 1 mole, then the delta H of the reaction, if it is 30, that will be same as delta H of formation of H2SO4 liquid. Okay, so this is the equation for delta H of formation of H2SO4. Similarly, for formation of oxalic acid, so it should come from H2, carbon should come from graphite, oxygen should come from O2 gas. So this delta H of reaction will be same as delta H of formation of oxalic acid. Same goes through H3PO4. H3PO4, H2 is coming from H2 gas, hydrogen is coming, phosphorus is coming from P4 solid white, and O2 is coming from O2 gas. Here also, delta H of the reaction is equal to delta H of formation of H3PO4 liquid. Next, if this is 6 moles of carbon, graphite plus 6 moles of hydrogen and 3 moles of O2, that's when I get 1 mole of glucose. So this one also, delta H of the reaction is equal to delta H of formation of C6H12O6 in solid state. Okay. This is how you should be able to figure out and write the chemical reaction for any particular uh, substance. Clear, everybody? So, just as a sake of practice, immediately now you will write few more examples here quickly. You can take this as a reference one and try writing these examples now. Please write down. First, write delta H of formation reaction for KClO3, delta H of formation for, you know, Cu, uh, sorry, barium iodide, IO3 twice, delta H of formation of, you know, K2Cr2O7 in solid state, delta H of formation of S2O3 thiosulfate solid. Quickly write down for these cases. Check if you got them correct. First will be potassium solid plus half of Cl2 gas plus 3 by 2 times of O2 gas. That must be giving 1 mole of KClO3 solid. So this will be the reaction which will describe the formation of ClO3 solid. Second one, barium in solid state plus 3 moles of O2 in gaseous state plus 1 mole of I2 in solid state, that giving away BaIO3 twice solid. This will be delta H of formation of Ba iodate, right? Barium iodate solid. Clear? Next, K2Cr2O7. So K solid 2 moles plus 2 moles of chromium solid plus 7 by 2 moles of O2 gas. That is giving K2Cr2O7 solid, which is orange color crystals. So this orange crystals of K2Cr2O7 solid is what we are representing. Next, lead is a solid form. Okay, 4 times of, sorry, 1 by 4 times of 1 by 4 times of S8 rhombic solid. Okay, that plus 3 by 2 times of, okay, O2 gas. This will give you lead, you know, uh, thiosulfate, lead thiosulfate solid. So this will be delta H of formation of PbS2O3 solid. Delta H of OH minus. See, there are two ways I can write: H plus aqueous plus O2 gas of half of it. And you know that there is electrons also, because I need to get an OH minus here. Okay. Left hand side I have H plus. So I need to add two electrons here so that it can become, you know, it can become OH minus. Now you can see the charge will also be balanced. So this will be delta H of formation of OH minus aqueous. This is one way of writing it. The other way is you can directly take H2 gas plus half of, sorry, yeah, half of O2 gas plus 2 electrons, sorry, plus one electron will give you OH minus aqueous. Okay, this is a theoretical way of writing. You will not see exactly practically this kind of reaction is actually possible, isn't it? You will not see this reaction is possible to give OH minus, but theoretically when you're writing delta H of formation, this is what you can write. Both of them are correct. For water, what is correct? For water, it is going to be always H2 gas plus half of O2 gas. That would give us H2O liquid, and this will be the delta H of formation of H2O liquid. And delta H of formation of O2 minus. So therefore, it is O2 gas plus 2 electrons is somehow becoming O2 2 minus gas. Okay, sorry, O2 minus. O2 minus. So this is half. So this will be the delta H of formation of O2 minus gaseous form. Please check your answers. I'm hoping that all of you got the same. And everybody? Now, sorry. Now let's closely observe what are all the applications of this delta H, starting with standardized values as well as general delta H reaction values. First, let's start with standard heat of combustion. This is the first application. Okay, let me call this as first application, which is standard heat of combustion. This is how we represent delta H naught. When I'm using the word standard, that means there should be naught here of combustion. This is done for 1 mole of a substance. We are always need to discuss delta H of standardization for 1 mole. Next, we need to provide sufficient or excess amount of oxygen for reaction to happen. And here heat must be released. Okay, this is a necessary condition. This is a necessary condition. Then only we call it as combustion. If heat is not evolved or heat is been absorbed, then it is not a combustion reaction. Okay. And lastly, I mean, of course, this is just the explanation of that. Exothermic change should happen. That means heat has to be evolved. Okay. Check out this for example. H2 plus half O2 to give H2O liquid. Okay. This we learned earlier as delta H of formation of H2O liquid. But it is perfectly fitting in the definition of combustion also. So you can see H2 is giving sufficient amount of oxygen to get H2O liquid. So you're taking 1 mole of H2. So therefore, this can be read as this is the combustion of H2 gas, which is same as delta H of formation of H2O liquid. Clear? This is a definition from both ends. One is with respect to combustion, one is with respect to the formation of water. Similarly, graphite also. Graphite plus O2 giving CO2 gas. This is combustion as well. Combustion of graphite. But at the same time, it is also delta H of formation of carbon dioxide. Okay. Similarly, you can see if you have this as glucose plus O2 giving CO2 and H2O. Only if delta H naught is less than 0, that means it is exothermic, then we call it as combustion. So this is delta H of combustion of glucose. Okay, delta H of combustion of glucose, which is same as delta H of this reaction. Okay, clear? Right. Now, N2 plus half O2 giving N2O, it looks like combustion except that delta H of the reaction is coming out to be positive. If delta H of the reaction is positive, which means it is definitely not combustion. Okay. Similarly, F2 plus O2 forming F2O2 is also a delta H being positive value. Second thing, carbon plus half O2 is giving carbon monoxide. This is exothermic, but this is not combustion. Why? Because oxygen used is not sufficient. If you'd have used sufficient oxygen, this would have converted into CO2 and not in CO. So you need to check out to maximum oxidation, how much it can go. Carbon can go up to 2 oxygen combinations. So therefore, this is also not a combustion reaction. Sulfur plus O2, if at all I'm providing excess and it is becoming SO2, right? But how much moles of sulfur I'm using? 2 moles of sulfur I'm using. So if I use 2 moles of sulfur, then also it is not combustion. It is, if this is delta H of the reaction, the combustion of sulfur will be delta H of the reaction by 2. Boys, clear on that? Any doubt here? Right. Now, let me come back to these questions. First, let me explain what is calorific value. Calorific value is how much amount of combustion that is being observed, that is heat released per gram of the substance. If this is your fuel, and if you divide it by molar mass, then you will get what is its CV value. Okay. And if the CV value is more, correct, we can always relate this as CV, calorific value, is directly proportional to quality of fuel. Quality of fuel, whether it is a good quality or bad quality, and so correct. We can always refer to quality of fuel. Check it out. If C is, first one thing, C is just a magnitude of it, so it is always positive. H2 has the maximum value because the molar mass of H2 is the least. And for example, if you take CH4 and C2H6, then the calorific value of the organic compound having more hydrogen oxygen ratio. Here the ratio of hydrogen oxygen is 4 is to 1. Here it is 6 is to 2. So which is 3 is to 1. So more the number of hydrogens, more is the calorific value. And more calorific value, which is better quality of fuel it is. More efficiency it is. So it is also proportional to show that it is efficiency. In fact, better quality is always going to be increasing the efficiency. Got it? And you see that if you have to figure out number of, I mean, delta H of combustion is also dependent on number of carbons. Okay. So if more the number of carbons, more is the delta H of combustion. So for example, if you compare the combustions, definitely combustion is increasing. But at the same time, the uh, quality of the fuel keeps decreasing. That means the calorific value will start decreasing. Okay. So delta H naught of combustion is inversely proportional to branching. This is for their isomers. So these are the cases. For example, A, B, C we have. The lower the branching, less will be the energy released. And this will release more amount of energy. Combustion case is clear, beta? Right. Now these are two important terms that are used while solving questions. See, if at all we are making combustion at a constant volume, that means you are heating a organic substance or any compound at a constant volume. Okay. Usually if you are using an instrument where the combustion is happening but the volume of the container is not changing, then that particular container is called as bomb calorimeter. That is called bomb calorimeter. And if the combustion is happening at a system which is operating at constant pressure, that means the volume can keep increasing or decreasing, but the pressure should remain constant. Such a kind of instrument is called cup calorimeter. One is bomb calorimeter, the other one is cup calorimeter. So if this terminology is used, bomb calorimeter or cup calorimeter, it refers to delta U and delta H. Everyone clear on that? Right. Now let's go back to the questions, how that can be framed and see the language of the questions. So emphasize more on the language of the question. Check out. 1150 kilocalories heat is released when reaction is carried out at constant volume at temperature given. So I think that data is sufficiently, I mean, very straightforward data. We don't have to worry about that. Reaction is also given. You just need to figure out the heat exchange at constant pressure. What do you mean by heat exchange at constant pressure? It means delta H. Simply, we are talking about delta H. So how do we solve it? See, delta H is equal to delta U, okay, plus delta Ng RT. And delta H in this case, that is what we need to follow. And this much amount of heat is given carried out at constant volume. So delta U is given 1150. This is 1150. Carefully observe that this is given in kilocalories. So we need to make sure the other terms are also in kilocalories. Now, what about the number of moles? So product side, there are 7 gaseous moles. This is liquid. Here we have, 11 gaseous moles. This is liquid. Okay. So 7 minus 11. So that makes it minus 4. So therefore, we have it as minus 4 into 8, because 1150 is in kilocalories. I will multiply that with 2. So 2 represent that you are representing R in calories. Temperature is 273. In Kelvin scale it is 300. But another problem, this is kilocalories, but this is in calories. So how do I convert it? 10 raised to power of minus 3. So now everything is in kilocalories term. So that will be equal to 1150 minus this is 600, 2400. So 2400 into 10 raised to power of minus 3, which is 1150 minus 2.4. Right? So that will become, this is equal to 11.47.6. Then, so this much kilocalories is the delta H value. Please check, everybody. If you have any doubt, you can ask me now. Right? So consider, if you understand that, apply the same logic to the next question. Everybody, try it out. 37.5. Yeah, perfect. That's right. Both of you got it right. So H2O vaporization implies that we are trying to make it from H2O liquid to H2O gas. So the minute you start getting anything in a gaseous state, you assume it to be ideal. So in that case, delta Ng will be equal to 1. So delta H, which is equal to delta U plus delta Ng RT. So the value of delta U naught is what I need to figure out, which is equal to delta H naught minus delta Ng RT. Okay. Now delta H naught will be equal to 40.63 minus delta Ng is 1 into, because this is in joules, so I'll make this one also into joule units, into temperature is 373 kelvins, but this is in only joules. I need it in kilojoules. So 10 raised to power of minus 3. This is what you will supposed to get. So on solving it, you will get this as 37.5 kilojoules, right, is the value. Here is an interesting question in the same question, guys. Suppose if the question was given like this, okay, for 10 moles of the vaporization value, it is 400.63. Correct? Clear? Now I need to find out what is the delta U value in this. What will you do? Suppose the same question is asked, but initially for this is given for 10 moles and you are supposed to calculate what is the delta U value. So make sure first, every time you get delta H value, convert that into 1 mole and then only apply this formula. Okay. So because delta H and delta U both should be applied when you have both being asked at 1 mole of that substance. And once you get that for 1 mole, then again once you get delta U, again you multiply that with 10. So you'll get for the entire reaction how much will be the delta U value. Got it? So just be aware if the question is asked that way. Let's see the next question here. For a gaseous reaction, which is mentioned, delta H naught is mentioned, at what temperature it is mentioned. Calculate delta U when 1 mole of SO2 is completely reacted with 1 mole of O2 in a 10-liter rigid vessel at an initial pressure of 50 bar, which decreases to 20 bar. Okay. The rigid vessel itself, gives you an assumption that it is happening at constant volume. Take your time, try to right. See, check it out, guys. No worries. See, first, as per the question given, this is for 2 moles. Yeah. So this entire data is given is for 2 moles. So for 1 mole, how much it will be? For 1 mole of SO2, delta H would be equal to minus 220 kilojoules per mole. I got to use this. And I took 1 mole each. So obviously some amount of moles will be left here. So 1. It looks like SO2 is limiting. So zero point 0.5 will be left here. And how much 1 mole will be made here. Correct? Clear? But it doesn't matter. The reaction is happening. Now I need to find out delta H, which is equal to delta U plus delta of PV. This is how it started actually. Okay. But here temperature information, all of that is not there. So do you think we should be using this formula, delta NGRT? Because temperature is not known. So it's not better to use this. Pressure terms are given, volume term is given. So I can simply use that. I told you it is a rigid container, which means the volume always remains constant. So volume can be pulled out. So it is only about delta U plus V delta P. Okay. So that implies delta H, which is equal to minus 220, is equal to delta U plus V delta P. What is our rigid volume here? 10 into how much is the pressure being changing? So from 50 to 20 bars. So 20 minus 50. Okay. This is what it should have been. Clear? And now from here I can write delta U is equal to minus 220. This is in kilojoules. Yeah, kilojoules. So that minus this will be minus 30. So minus 30 into 100 is minus 300. If I take it to the other side, it will become plus 300. Okay, clear. And this is given in what? Liters and bar units, isn't it? Liters and bar units, if you have, how do I convert that into joules? By multiplying that with 100. And how do we make it in kilojoules? By multiplying that with 10 raised to the power of minus 3. So what do we have? Minus 220 plus 30. This is what we have. So how much we are getting? Minus 190 kilojoules is the final answer. Check.
Sir,
Yes, Vita.
sir, why didn't we use NRT, the delta U plus delta NRT?
All right, Vita. Delta U plus delta NRT. We can use it, but as it everywhere, anywhere mentioned that, sorry, when you have delta NGRT here, we assume the fact that the reactants have been completed. Got it? Understood. So is it a complete reaction that is happening? No.
No, sir.
Okay. So the only way we can assess is on the basis of their volumes and uh, pressures. Clear?
Yes, sir.
Finish everybody. Right. Now let's go to the second term. First application we learned is delta H of combustion. Now let's talk about the second application. The second application is about bond dissociation energy. Okay, let us understand what is bond dissociation energy. When we are using the term bond dissociation energy, it implies that how much amount of uh, energy is required to break a bond. Okay, so it is always a positive energy. That means energy is required here, right? It is endothermic, and delta H of the reaction is always positive. Okay, it is always about breaking 1 mole of similar bonds. 1 mole of similar bonds. That means we are talking about an average. For example, if I take CH4, right, and I heat it here, so I will get this as, I'm heat in a sense, I'm providing energy here to break this CH4 into CH3 plus H. So energy is required here. Let's say the required energy is delta H1. Same way again, I'm breaking carbon hydrogen bond, removing the second hydrogen. This much is the energy required. Third case this much, fourth case this much. So if I write the overall reaction here, that will become CH4, sum of these four, is equal to C plus 4H. See, when you sum all the equations, chemical equations, their energy will always get added up. So the addition of all these four is delta H of reaction. Okay. So here also you are breaking CH bond, here also CH bond, here also CH bond and CH bond. So that means on an average, what is the energy that you are actually using to break one CH bond? That is bond dissociation energy. And it is usually represented as epsilon CH, which means it is a mean bond enthalpy that is equal to summation of all these four energies divided by 4. Okay, so this is the average amount of energy required to break the bond. Clear? Right. Now I can say that for any chemical reactions, when we talk about chemical reactions, we say that delta H naught of the reaction is formation on the product side minus formation of the enthalpies on the reactant side. Correct? Same way, if you write it in terms of, bond dissociation energies, then we can write down that as summation of all the bonds on the reactant side minus summation of all the bonds on the product side. Okay, this is in terms of formation. This is in terms of product form. This is in terms of products. Okay. Before I explain you what is atomization, let me let me tell you how you need to think in terms of uh, delta H of formation and delta H of, sorry, bond dissociation energy with an example. Okay. Let's see. Let us talk about a simple example like N2 gas plus 3H2 gas is giving 2NH3 gas. Correct. So if at all I write delta H of this reaction, then delta H of the reaction is enthalpies of the product minus enthalpies of the reactant. So that means I can write delta H of the reaction is equal to 2 times delta H of the formation of ammonia plus 1 time delta H of formation of nitrogen plus 3 times delta H of formation of hydrogen. Okay, this is delta H naught of the reaction, standard enthalpy of the reaction. Got it? Now, if you notice that this term is 0 and this term is also 0, so it is simply 2 times of delta H of formation of ammonia. This is delta H of formation of ammonia. Okay. Now, suppose if at all I have to calculate what is the formation of nitrogen atom. So, can I write this equation as N2 gas, yeah, N2 gas giving 2 nitrogen gas. Okay. So, if I write in terms of delta H of formation, can I write this as delta H of reaction here, right? It is equal to delta H of formation 2 times of delta H of formation of nitrogen. Similarly, if at all I write H2 gas going into, 2H gas, then I can write this delta H naught of the reaction is equal to 2 times of delta H naught of formation of hydrogen. This is what we can write. Similarly, if at all I write delta NH3, right, as N plus 3H, then also delta H of the reaction is equal to delta H of formation of nitrogen plus 3 times delta H of formation of hydrogen. This is another way we can write. Clear? So far, I'm just sticking to the definition what we have learned. Correct. Now, I need to somehow get this equation using this 1, 2, 3. These are the equations. Let's say I have equation 1, equation 2, equation 3. Okay. I need to use these three equations to get the first equation. I mean, which is our general equation. So, which means I need to multiply the second equation with 3 first. That is the first thing I need to do. So, this equation 3, I need to multiply 3. And then equation 3, I need to multiply with 2. And thereafter, I have to add these two equations and subtract the third equation, correct? So, just think in terms of addition and subtraction of the equation. So, 1 plus 3 times of 2 minus 2 times of 3, third equation. That would give us N2 plus 3H2 is giving 2NH3. Now, in terms of energy, what is that you're adding? You're adding 2 times of delta H naught formation of nitrogen plus 6 times delta H naught formation of hydrogen minus, how much is this one? Minus delta H of formation of nitrogen here, correct? This one, because I have to break this nitrogen and 3 hydrogens here. So that will be equal to delta H of formation of nitrogen. Oh, sorry, minus. I forgot to write the minus here. Minus, okay, minus delta H of formation of NH3. Okay. Earlier, I didn't write for nitrogen, I didn't write for hydrogen because they were 0. Correct? Because they were 0, I didn't write down. Here, ammonia is not 0, so I have to write that. Clear? So this will bring us delta H of formation. I need to multiply this equation with 2. So multiply that 2 here. So this will be equal to 2 times here. So what I'm writing is the delta H of the reaction. Delta H of the reaction. This is delta H of the reaction. So for that, minus 2 times of delta H of the reaction, minus 6 times of delta H of formation of hydrogen. Clear? And what about this one? This is plus delta H of formation of 2 times delta H of formation of ammonia. Correct? So what have you noticed that? So this 2 and this 2 will get cancelled. This 6 and this 6 will get cancelled. So delta H of the reaction is same as 2 times delta H of formation of ammonia. Is that clear? So I'm just trying to prove you the same point what we got earlier, isn't it? Delta H of the reaction is 2 times delta H of formation of ammonia. Okay. Now let me introduce the definitions what we learned. What is the definition we learned? Check out. If you are breaking nitrogen N and N bond here, so that means this can be written as epsilon N triple bond N. That is what you are breaking, correct? So 2 times delta H naught of formation of nitrogen is epsilon N triple bond N. That is a bond dissociation energy of nitrogen. Similarly, this will be equal to epsilon H bond H, correct? And that multiplied by 3 here, because you are multiplying that with 3 here. So that into 3. Clear? And lastly, what about here? Here, now this will become epsilon half of, this is half of epsilon N triple bond N plus 3 by 2 times of epsilon H single bond H, that minus, what about N and H bond here? So I can write this as, you know how many bonds we have? 3 bonds. 3 bonds of epsilon, okay? Because your overall, this is the bond you're breaking, right? So 3 times of epsilon N and H bond you are breaking, correct? So in this reaction, so this is about the first one, second one, this is about the third one. So this entire thing, sorry, the last one, uh, this one I have to multiply that with 2. Okay. Now for the last one, this is the equation, correct? So let me just remove this part first. Right. So let me just simply write down here. This one. Okay. Use the same coloring. Epsilon 3 times of epsilon NH bond. Correct. Now to equate those to what we have done, we have multiplied this with 2. Now let me write everything in terms of epsilon, guys. So as per the equation, I have to add this and then subtract this. So what do I get? So that means delta H of the reaction, delta H naught of the reaction must be equal to epsilon of N triple bond N plus 3 times of epsilon of H and H, that I have to subtract with, 2 times of, 2 times of, okay, uh, sorry, 6 times of, 6 times of epsilon N and H bond, correct? Now this will give me what? Okay, delta H of the reaction. Have you noticed what is this one? Can I write this entire thing as, you know, summation of, you know, bond dissociation energies of the reactants minus summation of bond dissociation energies of the products. Okay, so I think I proved my point. You can go through this and check. This is what I'm trying to tell. So H naught of the reaction can be written in terms of formation of the products minus formation of the reactants, or another way of representing is bond dissociation enthalpies of the reactants minus bond dissociation enthalpies of the products. Correct? So is that point proved here? Please check. So you could represent delta H of the reaction both in terms of uh, formation values or in terms of bond dissociation values. Is this clear? Now, see what exactly is atomization. Okay, check out what is standard enthalpy of atomization. Okay, so 1 mole of substance. If I take 1 mole of substance, clear? For that 1 mole of substance, how much amount of energy is required to break everything into atoms, right? So, for example, all the products must be in gaseous state, clear? So, that means if I take CH4 in a gaseous atom, gaseous molecule, you have to convert all of this into gaseous atoms now. So, C gas, 4 hydrogen gas. Clear? Check. CH4 is giving out C plus 4H, and the amount of energy required is delta H of atomization. Next, delta H of atomization of methane is equal to 4 times, you know, because you notice that we are breaking basically 4 same bonds, so that is equal to 4 times of epsilon CH. Okay, and now check it out. H2 converting into 2H, that is also an atomization. So for a simple diatomic molecules here, I mean diatomic species here, you will always notice that the atomization and the delta and the bond dissociation energy will be same. So delta H naught of atomization of H2, that will be epsilon of HH. Clear? Understood what is standard enthalpy of atomization? Right. Acha, what is the difference between bond dissociation energy and atomization? See, one good example here we can take is about bromine. Okay, let me show you with an example here. See, suppose if at all I have Br2 liquid converting into 2 Br gas. Okay, let's say this is delta H of the reaction. So can I say that delta H of the reaction is equal to uh, epsilon of Br and Br, considering I'm breaking the same bond, Or can I say that it is delta H of atomization of Br2 liquid? Or can I say this as delta H of, you know, delta H of vaporization of Br2 liquid plus delta H of atomization of Br2 gas? Or can I say this as delta H of vaporization of Br2 liquid plus epsilon of Br and Br? Which of these four statements looks correct when I write delta H of the reaction as this way? Br2 is converting into 2Br in gaseous state. Now listen up. Bond dissociation energy, whenever we are defining, it is only defined when your reactants are gases. You're specifically asking about the bond, so that means they should not have any other affinity. The molecule should not have any other affinity with other molecules, which means you will expect that to be in a gaseous state. So can the first one is correct? Is the first one correct? No, because reactants are in liquid state. So this cannot be correct. But can I say it is the atomization of Br to liquid? Absolutely, because you're considering that in liquid state. And atomization does not tell you that the reactant has to be in the liquid state, gaseous state, or solid state. It definitely emphasizes that the products must be in gaseous state, which it is there. Clear? So this one is correct. Or I can do one more thing. The same reaction can be break down into two things. One is Br2 liquid first converting into Br2 gas, and then Br2 gas is finally converting into 2Br gas. Obviously, here the energy required, because liquid to gas, is called as delta H of vaporization. And here from Br2 to 2Br, the amount of energy that is required is epsilon of Br and Br. Or you can write it as delta H of atomization of Br2 gas. So that's why these two statements are also correct. Clear with the definition? Okay. So please do understand what is these two terms, how they are different. One is bond dissociation energy. The other one is standard enthalpy of atomization. Clear? Okay. So that is what I have written it here. You can see it. Okay. If at all I have delta H of formation of, carbon gas to be found, atomization is given, formation of oxygen is given, formation of carbon monoxide is given, and 100 and minus 114 kilojoules per mole is given. Then how do we figure out how do we calculate delta H of formation? Okay. So let me take this one case and then we will close it for today. So please let me check. Let me show you this. How do we solve it? Every time this kind of questions are given, first try to write down the given data in terms of chemical equations. That will make it very easy. So this is given atomization of carbon monoxide. So check out, CO gas is converting into C gas plus O gas. So for this, delta H of atomization value is given. Okay. Second, formation of O2, which means O2 gas, half of O2 gas is converting into O gas. This is the formation of O. Okay. This one is given as well. Next is carbon monoxide, formation. So CO, carbon monoxide, from where does it form? It will form from C graphite in solid state plus half of O2 in gaseous state. These are their elemental forms to get it into CO gas. So for this, the formation is delta H of formation is given as CO. Okay, I mean, this is the value which is given, right? Now the question is, what is the formation of carbon? How do we get formation of carbon? If graphite solid, right, is converting into C gas, that is the formation of gas. So this is delta H of formation of carbon gas. Okay, all I'm doing is whatever the information that is given, I'm just writing them in equations. That's the best strategy for solving these questions. Okay, as you start becoming more familiar with these questions, it becomes easier to visualize. You don't have to write the equations also. But yeah, nevertheless, at the starting point, it's always better to write all the equations. And now it's very easy to converse with these equations. See, 1, 2, 3, and 4. So I'm supposed to get 4 using 1, 2, 3 equations. How would I get that? See, graphite should be on the left hand side. So third should be on the left hand side. Okay. Carbon should be on the right hand side, which is what we will get it from the equation 1. Okay. So this CO can get cancelled. And I need O and O should be also supposed to cancel, and this should be getting cancelled. So 3 should be 2 should be subtracted from 3 for sure. Sorry. Which means I need to take 3, add 1 and subtract 2. That's the best bet we can do. Correct? Notice everybody. So this is the best thing we can do. So that way things will get cancelled very easily, and the equation will be what we desire. So therefore, delta H of formation of carbon gas will be equal to 3. For 3, formation of CO is given minus 114 plus 1. 1 is given as 1072 minus 2. 2 is given as 247. 247. That's it. This is the value you will get. Clear? I suppose you guys understood how to deal with bond dissociation energies and these terms, formation or atomization terms. Correct?